Hello everyone, welcome back to Algebra. Today we're going to be talking about the consequences of the class equation. So just to remind you, in the previous video we proved what we call the class equation, which is the following. Suppose we have a finite group G, and G is acting on G. There's a group action of G on G via conjugation. Then the size of the group is equal to the fixed points via the action, which is in this case is equal to the center, those elements of G that commute with everything, plus the sizes of the non-trivial orbits. It's the sizes of the non-trivial conjugacy classes. And here I pick G1 through GR to be representatives of those non-trivial conjugacy classes. Now, we also saw the orbit stabilizer theorem, and you can eventually, we proved that the orbit, the size of an orbit, is equal to the index in G of the stabilizer. And then we saw that the stabilizer in this case is the centralizer, which is defined as follows. The centralizer of each one of those representatives of a non-trivial conjugacy class. So either in this shape or in that shape, that's usually referred to as the class equation. Something very important to note is that these orbits are equal to these indices, and these indices, by Lagrange's theorem, are divisors of the order of G. So these numbers here and this one, because this is a subgroup of G, each one of those is a divisor of the order of G. So this is a very interesting equation that is writing a number as a sum of divisors of that number, and that is pure number theory. So we're going to be able to use things like divisibility to give conditions on that are going to be coming as a result of this. For example, let me give you one example, is that if S3 is acting on S3 via conjugation, then we have the class equation for S3 is the following. The center of S3 is identity. Nothing commutes with everything except for the identity. And there's two non-trivial conjugacy classes. The conjugacy class of 1, 2 is conjugate to the other elements of order 2, and the conjugacy class of 1, 2, 3. 1, 2, 3 is conjugate to the other element of order 3. So these are the two conjugacy classes, and the class equation reads 6 is 1 plus 2 plus 3. Which is interesting on its own, that 6 is the sum of its proper divisors, which is actually a proof that 6 is a perfect number. But in any case, this is what the class equation says. So let me give you a couple of consequences of the class equation. I want to prove a couple of theorems about groups that we didn't know before, and it's all going to be consequences of this class equation. Let's see. The first theorem I want to prove is the following. Let G be a group of order p to the n, where p is prime. Then G has non-trivial center. So there is something in the center, there is something that commutes with everything. So let's see why this is true. We're going to let G act on G via conjugation, and therefore the class equation reads, the class equation is going to read that the size of G is the size of the center plus, and I'm just going to call N1 plus NR are going to be where the NIs are the sizes of non-trivial conjugacy classes. And as I said just a moment ago, note that each one of those is a divisor of the order of the group for I1 up to R. Okay? And since the order of the group is a power of P, that implies that each one of those NIs is a power of P, something like this. But in particular, what I have is that P does divide Ni. They are non-trivial orbits, so each one of those uh, are bigger than 1. They're non-trivial, so each one of those Ni's is a multiple of P for all I 1 through R. And then what I have is that the order of the center is the order of the group minus N1, let me write minus, 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 minus NR. This is a power of P. These are all divisible by P, so they are 0 modulo P. So everything is 0 modulo P, and therefore the order of the center is 0 modulo P. But it is not 0. The order of the center is at least 1 because we have an element in the center, namely the identity. Therefore, P does divide the order of the center, and in particular, the center is non-trivial. Thus, the center is of size of order at least P, and so it is non-trivial. QED. So that's what I wanted to prove. Notice that that is actually stronger than what the statement says. The statement says that G has non-trivial center. What I've actually proved is that the order of the center is at least P. So if P is 2, then I'm saying there's at least 2 elements, so that's just non-trivial. But if P is bigger than 2, then it's saying I have, at least P elements in the center, which is something interesting. So this is one consequence of the class equation. Let me show you another consequence. And the second theorem I want to prove is the following. Let G be a group of order P squared, where P is prime, then G is abelian. That is very interesting because we didn't know that, for example, every group of order 9 is abelian, or every group of order 49, 25, that all of those are abelian groups. So let's see why this is true. So here's the proof. Let's start with by looking at the center. Let G be a group of order P squared. Then by where P is prime, by our previous result, we've just proved that if the order of the group is the order of the group is a power of P, then it has non-trivial center. So the center is at least of order P. It is a subgroup. So we can say that in fact the center is non-trivial, and the order of the center has to divide P squared. So it is P or P squared. If the order of the center is P squared, then G is equal to its center, and then it means that everything commutes, and therefore G is abelian. And the claim is that the center cannot be of order P. So let's assume that the order now of the center is the other possibility, that it has order P. If it has order P, then we actually have that the center has order P, and the group modulo its center, which is in fact, the center is normal, so this is a group. Then the group by Lagrange's theorem, it will have order P squared divided by P. It is a cyclic group of order P. Thus, G modulo the center is cyclic of order P. So it has a generator. So let a z, I'm just going to write z for the center, be a generator of the the cosets of z in G. Then, okay, so let's recap that. We have that G modulo the center is generated by some element, some coset, A times Z, where A is some element of G. And now let G and H be elements of G. I want to show that they commute, so I want to show that GH is equal to HG for arbitrary G and H. So let me start with G. Well, G itself times Z, that is a coset, so it has to be some power of the generator. It has to be AZ to some power M. And by the way multiplication works in cosets, this is A to the M times Z. But then what that means is that G is in this coset, and therefore G is some power of A times something that is in with X in the center. Okay, great. But similarly, H times that coset will also be generated by these cosets. So there will be some power n such that A to the n times that coset gives me the coset generated by H. And that tells me that H itself is A to the n times some y for some y in the center. Then how much is GH? I'm hoping it's H times G. So G is A to the M times X, H is A to the N times Y. And now the magic happens because X is in the center, so X commutes with everything. So I can write A to the M, A to the N, X, Y, which is A to the M plus N by the rules of exponents. And now I can change that to be A to the N times A to the M X Y. And I can actually also, Y is in the center, so I can, it commutes with everything, so I can move the Y to this side. And now A to the N times Y is H, and A to the M times X is G. So we have proved that GH equals HG, which is exactly what I wanted to show, because then G is abelian, but that is a contradiction because then that would say that the size of the center is P squared, which is not P, which is what we had assumed in this case. So the order of the center must be P squared regardless, and then we have proved that the group itself must be abelian. So this is a strong consequence that it says things like, as I said, that if you have any group of order 25, then G must be abelian. And by the classification of abelian groups, then we know that G must be isomorphic to the cyclic group of order 25, or it is isomorphic to two copies of Z modulo 5. So it completely classifies every single abelian group of every group of order P squared, because if this was just P squared, then G is abelian, and then it has to be Z modulo P squared or Z modulo P cross Z modulo P. So that's a very nice consequence, and it's a consequence of the class equation. So next, we're going to start our study of Sylow subgroups and the Sylow theorems. So in the next video, I will just do an introduction of why are we doing this, why do we care about Sylow groups, and where we are going with those. Bye-bye.